Hello everyone. In this video we are going to see about the subject control system unit 3 frequency response and system analysis. In that the topic is Nyquist plot. Objectives. At end of this video we gain a knowledge of about various methods for analyzing the frequency response and the stability of the systems. Nyquist plot. First, what is meant by Nyquist plot? The complete version of the polar plot is known as the Nyquist plot, or we can say the extension of the polar plot is known as the Nyquist plot. The main difference between the polar plot and the Nyquist plot is that the polar plots are based on the frequency range from 0 to infinity, while the Nyquist plot are based on frequency from minus infinity to plus infinity. After that, the Nyquist criteria help us to determine the closed loop system stability from the frequency response of the open loop poles. After that, by using the Nyquist plot, we will detect the presence of closed loop system poles in the right half of the S-planes for what means to determine the system stability. It is because the Nyquist plot relates the open loop frequency response to the number of poles and zeros of 1 plus g of s into h of s that lie on the right half of the S-plane. So these are all about the introduction of the Nyquist plot. After that, we have going to see the what are the steps we have to follow to draw the Nyquist plot. The first step is we have to determine the poles and zeros. How means from the given transfer functions we need to determine the poles and the zeros for what means whether to check the points are valid or not. After that, we have to selecting the Nyquist plot. In this, we have to consider the singular points. These singular points are the points lying on the imaginary axis. Generally, the singular points are avoided. After that, if the transfer function has a pole at 0 or origin, means the contour encloses all the poles and zeros except the origin. After that, we have to mapping a contour. A singular point, that means a point on the imaginary axis, it is not analytical. Hence, it is generally avoided. The Nyquist contour is mapped to determine the encirclement of the point minus 1 plus j0. Generally, the contour is drawn based on the transfer function of g of s into h of s. In the Nyquist plot, there are 4 sections, namely C1, C2, C3 and C4. The Nyquist criterion plot is divided into 4 sections so that the process can be easily carried out section wise. Range for the section, that means our first section C1, the value of omega in section C1 ranges from 0 to infinity. After that, the contour will be drawn in h of s into g of s plane with respect to the above range, and it will be the locus plot of g of j omega and h of j omega. And after this completion of first section C1, the range for the second section C2. The second section is generally of infinite radius. Here it is a semicircle of infinite radius. The range of the second section is from minus 90 degrees to plus 90 degrees. After that, range for the second section C3, the value of omega ranges from minus infinity to 0. After that, the section C3 is the just inverse of the polar plot of g of j omega into h of j omega. The resulted plot will be the mirror image of the polar with respect to the real axis. After that, range for the second section C4. The argument for the fourth section varies from minus 90 degrees to plus 90 degrees. The Nyquist contour for this section has a semicircle of 0 radii. After that, we are going to see about one example. The question given is, draw the Nyquist plot for the system whose open loop transfer function is given by g of s into h of s equal to k divided by s into s plus 2 into s plus 10. Also determine the range of k for which the system is stable. In the given example, we have to draw the Nyquist plot for the given function. Also, we have to find the range of k values. After that, we have to find whether the system is stable or not. Here, the first step, we have to write the given transfer function, that is g of s into h of s equal to k divided by s into s plus 2 into s plus 10. First step, we have to determine the poles and zeros. Since the transfer function has no numerator in terms of s, so there are no zeros in the given transfer functions. There are only 3 poles are present. That is g of s into h of s equal to k divided by, in this section we have to convert this in the terms of 1 plus s term. For this k divided by, we have to take 20 as common the outside. So s into 20 into s divided by 2 plus 1 into s divided by 10 plus 1. After that, then the step 2, we have to mapping of section C1. The value of omega in section C1 ranges from 0 to infinity. The contour will be drawn in g of s into h of s plane with respect to the above range will be the locus plot of g of j omega into h of j omega. So, we have to write again the given transfer function g of s into h of s equal to, that is 0.05 k divided by s into 1 plus, that is in the previous sections we have s divided by 20, that is 1 divided by 20 can be written as 0.5 s into 1 plus, in the previous we have s divided by 10, so we can written as 0.1 s. After that, we have to substitute wherever we have s terms, means just we have to put j omega. G of j omega into h of j omega equal to 0.05 k divided by j omega into 1 plus 0.5 j omega into 1 plus 0.1 j omega. After that, we have to factorize these two terms. We get 1 plus 0.6 j omega minus 0.05 omega square. After that, we can write like this: 0.05 k divided by minus 0.6 omega square plus j omega into 1 minus 0.05 omega square. After that, here we have no imaginary term, that is the imaginary term will be 0 and the resultant frequency will be our crossover frequency. Can be written as omega into, that is we have to equate this imaginary term into 0, equal to 0 means omega into 1 minus 0.05 omega square equal to 0. After that, omega equal to 0 and then 1 minus 0.05 omega square equal to 0. From that, omega value is 4.472 radians per second. This is our crossover frequency. After that, we have to put the value of the above frequency in the real part of g of j omega into h of j omega. So, in the given transfer functions, 0.05 k divided by minus 0.6 omega square. Already we have find the value of omega is 4.472. At last we get minus 0.00417 k. So, after that, from the given transfer function, we can easily determine the system is of type 1. How the system is type 1 means, we have one pole at origin, means this is our type number systems, and the given transfer functions is the order 3 systems. How means we have 3 poles in the denominator. That's why from the given transfer functions, the system is type 1 system and then order 3. After that, from this knowledge of type 1 and order 3, the polar plot will start at minus 90 degrees and crosses the point 0.00417 K on the real axis. This is our polar plot representations. Here type 1 system means this is our start of the systems. It will be start in type 1 and it will be insert the order 3 system, and it crosses the real axis at minus 0.00417 K. After that, mapping of section C2, that is from minus 90 degrees to plus 90 degrees. After that, if the transfer function is in the form of g of s into h of s equal to 1 plus 0.5 s into 1 plus 0.1 s, that is 1 plus st can be assumed as st. So it can be given by 0.05 k divided by s into, that is 1 plus st can be assumed as st. So 0.5 s in this term. After that, in this term we can just take it as 0.1 s. After that, we have 0.05 k divided by 0.5 into 0.1, that is we have 0.05. Here we have s power 3. After that, we have to cancel each other 0.05 in the numerator and 0.05 in the denominator. At last we get k divided by s cube. After that, the value of the transfer function at the specific value of theta will be, at theta equal to 90 degrees means we get e power minus j 3 pi by 2. At theta equal to minus pi by 2 means we get e power j 3 pi by 2. So from this, section C2 will vary from minus 270 degrees to plus 270 degree. This is our diagrammatic representations of section C2 in S-plane. After that, step 4, mapping of section C3. So the locus plot for the section C3 will be the increase on the imaginary axis at the same point as shown below. This is our diagrammatic section of C3. So this section C3 will be our inverse plot of our section C1, or it is the mirror image of the section C2. After that, mapping of section C4. The argument for the fourth section varies from minus 90 degrees to plus 90 degrees. The Nyquist contour for this section has a semicircle of 0 radii. After that, we have to find the stability analysis. For this stability analysis, we will find the value of k when the contour passes through the point minus 1 plus j0. Just we have to equate this terms into minus 1 plus j0 means we have minus 0.00417 k equal to minus 1. The value of k will be k equal to 240. This is our complete Nyquist plot after combining all the 4 sections are shown below. How we draw this complete Nyquist plot means, first, from the given transfer functions, we have a knowledge of it is type 1 system. So we have start in this quadrant and we have order 3 system. So it will be end in these sections. After that, this in the section C3, the radius will be, that is the omega value is minus 272 plus 270 degrees. After that, we have to draw the mirror image of the section C1 like this. After that, it crosses the real axis at the point minus 0.00472. This is our point. After that, the section 4, so just we have to draw the semicircle that is opposite to our section C1 and C2. This is our complete Nyquist plot after combining all the 4 sections. After that, we will find the stability at the 2 values of k. At the k less than 240 means it does not crosses the real axis and the point minus 1 plus j0 is not encircled. So the system at this value is stable. After that, k is greater than 240 means the contour crosses the real axis and the point minus 1 plus j0 is encircled 2 times in the clockwise directions. and there are no poles on the right half of the S-planes. At last, the system at this value of k is unstable. At last, the stability for the given transfer function, that is the value of k, is the range from 0 less than k less than 240. So this is our complete Nyquist plot representations and as well as the stability analysis. After that, advantages of the Nyquist plot. What are the advantages means this Nyquist plot are used to determine the stability of the control system, and also it can easily handle the time delay, and also Nyquist plot are used to find the frequency response of the open loop transfer functions, and also we have to determine the number of poles at present on the right side of the S-plane. And then one more most important advantages of Nyquist plot is we have to find the relative stability of the systems. These are all about the advantages of the Nyquist plot. After that, limitations or drawbacks of Nyquist plot. In the Nyquist plot, we can use some complex mathematical techniques. This is our first drawbacks of our Nyquist plot, and we have already seen in our advantages it is used to find the relative stability. So the Nyquist plot cannot determine the absolute stability of the system is the main drawbacks of our Nyquist plot. Also, it does not provide the exact information for what means how many number of poles present on the right side of the S-planes. So these are all about the limitations of our Nyquist plot. So these are all about the Nyquist plot. So these are all the references I used to make this video. Thank you.